Okay, this video is for Chem 2, Chapter 18, Reaction Rates, and we're going to be filling out a piece of paper that looks like this. So you should have this piece of paper in front of you, guided notes just like normal, and we will be filling out the front and the back in this video. Okay, so just to give you an introduction to what we'll be talking about in this chapter, up until... Well, no, let me back up. Okay, so we've been talking about things like whether or not a reaction is exothermic, releases heat, endothermic, takes in heat. We talked about if reactions are spontaneous or non-spontaneous with a calculation of delta G. We also talked about whether reactions increase or decrease in entropy, which is the randomness or the disorder in a reaction. But up until this point, we have never talked about the rate of a reaction. And rate, just like when you're talking about the rate at which you are traveling down a highway, has everything to do with speed. And so this is the first time we're going to be talking about the speed of a chemical reaction. And that's what the rate is. So the rate, in our definition, is going to be the speed of a reaction. And we know from, everyday knowledge that some reactions are pretty quick, like the reaction of baking soda with vinegar. It's a almost immediate reaction. But we also know that there are some chemical reactions that are pretty slow. For example, the rusting of iron. That's a very slow chemical reaction. And so there's definitely, it's definitely worthwhile to talk about and to study the rate of chemical reactions. Okay, so if we're talking about rates, which are just speeds, we need to talk about how rates are measured. And normally, I guess we should talk about units. So if you're talking about the speed that you're traveling down a highway, you're probably talking about miles per hour. It's a distance per time. Or I guess if you're in Europe, you're talking about kilometers per hour. It's still a distance per time. So obviously chemical reactions have nothing to do with a distance, but they definitely have to do with per time. And so in chemistry, the units of rate are going to be most of the time a change in molarity, which remember is moles per liter. So it'll be the change in the molarity of something per unit of time, which for us will be probably seconds. And so that's going to be the unit that you're going to be become very familiar with seeing. Molarity per time. Be very careful that you don't read this as meters per second, because it kind of looks like that. It's molarity per second. It could also be, molarity per minute. That's another acceptable unit for rate. It could also be molarity per hour. It could even be moles per second or per minute, although you're not going to see that quite as often, but it very well could be. Most of the time for us, we're going to be talking about rates in units of molarity per second. And we can talk about that in reactants or products, and we're going to get into that in a little bit. Okay, the next part of your paper says collision theory. So this is kind of just a very simple statement. I'll write it up here and then we'll talk about it, and I'll even show you kind of what I mean. Okay, so this idea of collision theory kind of governs whether or not chemical reactions will happen. And so collision theory says this: in order to produce an effective collision between molecules and thus have those two molecules go on to create products and then therefore have a chemical reaction. Those molecules must have two things. They have to meet these two criteria, or else we won't have an effective collision, which means we won't get any products. And obviously that means no chemical reaction. So the molecules must meet two pieces of criteria. One, they must have a correct orientation. And two, they must meet a minimum energy requirement. So the correct orientation sometimes gets students or throws students for a loop. But if you have any background in biology, one of the biggest places where this comes up is with enzymes and how enzymes almost fit together like puzzle pieces. So I actually brought two puzzle pieces. So here they are. And we're going to pretend like these are molecules. So if we want these two molecules to have an effective collision, well, they must meet each other with correct orientation. So for example, if they come and bump into each other like this, are we going to have an effective collision? The answer is no, because they're not aligned properly. If they come and butt into each other, say like this, are they going to have an effective collision? No. So no reaction. If they come and bump into each other like this, will they have an effective reaction? Yes, because now they fit together just like pieces of a puzzle. So that's what we mean by correct orientation. And even though that's a silly example, that's kind of how molecules work. So they must, one, have that correct orientation. They must fit together like puzzle pieces. And two, in order to have an effective collision and thus go on to produce products and have a chemical reaction, those puzzle pieces, if you will, those molecules, must collide together with a certain minimum energy. If they don't meet that minimum energy, the collision won't be effective and they won't turn into products. And so we're going to talk about that in more detail in just a minute. So collision theory says two things: molecules must have correct orientation and minimum energy to produce a reaction. Okay, moving on. Down our paper, we're now on factors that affect reaction rates. And this is kind of self-explanatory, but we're going to go over it quickly. And like I said, it's very simple. So we have four factors that affect rates or speeds of reactions. I'll do two of them at a time to save space here. And concentration. Okay, so next to the first bullet point that says physical state of reactants, I want you to put a slash, and then I want you to write particle size. Okay, so please add that to your notes as you're kind of heading at that first bullet point. So factors that affect reaction rates, there are four of them that are capable of changing the speed that a chemical reaction occurs. So the first one is the physical state of the reactants or their particle size. So for example, if you were to put and I think we've talked about this before, but it's okay, it's a good example. A sugar cube and granulated sugar into water. Well, we both know that they would dissolve eventually. But the question would be, which one would dissolve faster? And even though I know that's not a reaction, but we'll pretend like it. Which, quote unquote, reaction would happen faster? The dissolving of the sugar cube or the dissolving of the granulated sugar? I don't think it's a surprise to anybody that the granulated sugar would dissolve faster. Now, the question here is why? And the answer is because it has a larger surface area. So surface area meaning the amount of surface of something that, or in this case, the amount of the sugar that's in contact with the water, and thus the water is capable of dissolving it. If you think about a sugar cube, almost the whole contents of that sugar cube are inside. And so there's all this sugar inside the cube that does not contact or come in contact with the water until the outside edges are dissolved. So even though you think that a sugar cube might have a large surface area, it doesn't have as large of a surface area in comparison to granulated sugar as a whole, because if you think about one little granule of sugar, that whole thing comes in contact with water, and thus the water is able to dissolve it very quickly. So larger surface area equals faster reaction and thus faster rate. And again, I don't think that's a surprise to anybody. All right, the second one is the concentration of the reactants. So this one's very easy. Remember not my symbol, but the symbol for concentration is brackets, means molarity. So I'm just gonna do that and save myself some time here. So if we were to increase the concentration, so concentration increases, what do we think will happen to the rate? We got two choices. It's either going to get faster or it's going to get slower. The answer is it also increases. The question is why? Well, if we have more reactants, we have more possible collisions and therefore a quicker reaction. So why more collisions? Remember back in gases, the gas chapter, where a lot of our answers, it led back to the idea of collisions. It's kind of the same thing here, that anytime you can increase the number of collisions happening between your reactants, the faster the reaction is going to happen. So increased concentration, meaning you add more reactant, you get a faster reaction. You take some reactant away, you're going to get a slower reaction, for the exact opposite, that there would be fewer collisions. Okay, and the last two are temperature and a catalyst and an inhibitor. Okay, so how about temperature? Let's say we increase the temperature at which a reaction occurs. What happens? I don't think, again, it's a surprise to anybody, that the reaction is going to get faster. But why? Well, it's because there's an increase in the kinetic energy of the particles. If you increase the temperature, those molecules start moving faster. If they're moving faster, there are more collisions in a smaller amount of time, and therefore it's a faster reaction, faster rate. Again, the opposite is true. If you decrease temperature, we can even write this if you want. If you decrease temperature, then you decrease the kinetic energy of the molecules and you decrease the rate. So, and this is a great time to talk about the idea of refrigeration and why we refrigerate certain things. So all food is on a natural progression to eventually decay, right? Mold, rot, if you will. And so by putting food into a refrigerator where we are lowering the temperature and thus lowering the kinetic energy of the molecules, we're slowing them down, and so we're decreasing the rate at which that food is going to go bad, so to speak. And that's why we use refrigeration, to slow down the inevitable of the rotting of food. It's going to happen, but the refrigerator slows it down. And again, I think everybody knows that. All right, so last bullet point is the presence of a catalyst or an inhibitor. And these guys are opposite. So one speeds up and one slows down. You just have to remember which is which. So a catalyst increases the rate, and an inhibitor decreases the rate of a chemical reaction. So catalysts and inhibitors are actual chemical species. They're not the reactants, and nor are they the products. It's kind of like an extra thing that you might add to a reaction. And if you add a catalyst, you're going to make the reaction go faster. And if you add an inhibitor, you would make the reaction go slower. A lot of times catalysts and inhibitors come into play in medicine and in medicinal chemistry, because sometimes we need things to happen quick and sometimes we need things to happen slowly. And so we can change that rate by adding one or the other. So those are the four things: physical state or particle size, temperature, concentration of reactants, and then whether or not you have a catalyst or an inhibitor. Those four things can affect the rate of a chemical reaction. All right, little bottom section, we're going to talk about energy. Okay, so here I would like you to draw two, you can take up kind of the whole space, draw two graphs, and we're going to label them as energy versus time graphs, both of them. Energy versus time graphs. One of them we're going to draw so it looks like this. And one of them we're going to draw so it looks like that. So I'll give you a second to make sure that's on your paper. Okay, so from our discussion in thermochemistry, you should have no problem telling me a few things about these graphs. Let's start with one on the left. So right here, we are trying to represent the beginning of the reaction at time 0. So those are the reactants. And we're trying to represent over here, after some time has passed, the products, obviously. Same thing with the graph on the right. That's the energy of the reactants, and this is the energy of the products. All right, again, from our discussion in thermochem, we should be able to identify what this is, this change in energy between the reactants and the products. That's delta H, or Q, right? Enthalpy, heat of the reaction. And again here, the difference in energy between the products and the reactants, that's delta H, or Q, whichever you would prefer to call it. In this case, the products have less energy than the reactants, so energy had to be released. So this reaction on this side is an exothermic reaction. And over here, the products have more energy than the reactants, meaning energy had to be absorbed. So this graph is a graph of an endothermic reaction. Okay, let's focus just on the graph on the left for just a second. So we talked a little bit in our last chapter that reactions move in the forward direction, but they also move in the reverse direction. So in the forward direction, these are the reactants and these are the products, and this is delta H. Because this is an exothermic reaction, delta H would be negative. We don't know what value because we have no numbers here, but it would be some negative value. Now, if we were to read the reaction in reverse, meaning these would be my reactants, these would be my products, this is still delta H. The difference is still the same, except this time the reactants, going the other way, and the products, this time the reactants have less energy than the products do. And so in this case, going this way, the reaction would be endothermic and delta H would be positive. And this is where we get into that whole discussion of delta H being equal in size but opposite in magnitude for an exothermic going this direction according to this graph and an endothermic going this direction according to this graph. So all that you should know. That's all old stuff. Okay, a couple new pieces of information. I'm going to erase this so I have room to write. Okay, I alluded to this back in the thermochemistry chapter about the hill, the height of the hill from, so this hill that we're going to talk about is always from the reactants to the very top. So in this case, it's from the reactants all the way to the very top. And that hill is called the activation energy. Activation energy, and it gets the symbol E sub A. Energy activation. Okay, that's why the symbol is what it is. So the activation energy is the energy that the reactants need to collide with in order for the reaction to happen and the products to form. So this value right here, the reactants must collide with that amount of energy for the reaction to happen. In this case, they must collide with this amount of energy, which is much more than this reaction over here. And then the only other thing that I want to label is at the very top of the hill, I'm going to put a little asterisk at the very top. This is kind of like this weird transition state. That's actually one name for it. It's a transition state between the reactants and the products. Transition state. Transition state is one name. And it's, like I said, it's kind of this weird mesh of the reactants and the products. It's like when the reactants are colliding, but they have not really turned into products yet. That's called a transition state. It's also called an activated complex. So that's at the very top of the hill, a transition state or an activated complex. Okay, so one more idea here. Okay, so in looking at these reactions, the left reaction and the right reaction, I might ask the question of which reaction will happen faster? The left reaction or the right reaction? Which reaction will happen faster? And at this point, you might not know. You might be able to take a guess, but you might not know for sure. So the issue is reaction rate depends on only one piece of information that's being shown to you on this graph, and that is activation energy. Okay, so it has nothing to do with delta H. Absolutely nothing to do with delta H. So rate depends on activation energy. Write that down and put an exclamation point because it's very important. So this one has a smaller activation energy. This one has a bigger activation energy. This one has a little hill to climb. This one has quite a mountain to climb. Which one do you think will happen faster? Answer, the one with the smaller activation energy. So this reaction will happen faster than this one based solely on the idea that this reaction has a smaller activation energy. Activation energy tells you a lot about rate. Delta H tells you nothing about rate. So be very careful with that. So activation energy tells you everything about rate. Delta H tells you nothing about rate. It tells you everything about energy release or energy absorbed, but nothing about rate. Okay, so I said I was going to fill out the back of this paper, but I actually lied. So we're going to come to this in another video. So that's the end of the lecture for this video.